Welcome back. We were discussing the BJT amplifiers. Previous two lectures we have discussed on the common emitter amplifier and the common collector amplifier. So these two special type of amplifiers, which are again the BJT amplifiers, we have discussed. Now in the third part we will be discussing on the common base amplifier. So let us see what do you have on the common base amplifier when it is connected in the form of voltage divider biasing. We have seen that in the voltage divider biasing configuration, we will be having two resistors R1 and R2 that is connected in parallel in the base terminal. So here we will have in the common base, it will give high voltage amplification. So the voltage what we get at the output is high as compared to the input. The current gain is limited to 1. So it means there is no change in the current from the input to output, and low input resistance make it ideal for certain application and optimal for lower resistance sources. So in this circuit we can see the input which we are giving as AC supply, and the output that we get is basically the voltage amplification of the input. So output again we are collecting at the load resistor from the collector, and this is capacitively coupled. Whereas the input we are giving basically to the base and the emitter coupled to each other. The AC equivalent model of this common base amplifier will have the resistor at the output, which is a combination of the collector resistance RC and the load resistor RL, which are in parallel combination, and there is a current source which is the collector current, and we have two resistors which are defining the emitter. One is the actual emitter resistor, another is the AC resistance RE dash. So the voltage gain that we get it from the ratio of voltage output by voltage input. Output voltage we are measuring across the collector, and the input voltage we are measuring across the emitter. Collector voltage is given by IC into RC, whereas emitter voltage we get as IE, whereas RE dash is parallel with the resistor of the emitter. So approximately we can say that the voltage gain expression has this form. Since RE can be very greater than RE dash, so the final expression of voltage gain under such scenario will be RC by RE dash. The voltage gain, if we observe, then it is same for the common emitter amplifier. There is no phase inversion as we have observed from the emitter to collector in the common emitter configuration. So common emitter configuration, we have seen that there will be phase inversion, but here we don't have any phase inversion. Similarly, we can calculate the input resistance of the emitter, which is input voltage by input current. Input voltage we are taking in the emitter, and our input current we have the emitter current. So this is what our expression we have in input resistance. So the emitter current will cancel out each other, and if the emitter resistance is greater than RE dash, then approximately we can say that the input resistance is nothing but the emitter resistance itself. Output resistance approximately you will be getting at the collector resistance, and the current gain approximately it will be 1. So there is no change in the input current to output current. So the power gain, if we talk about, then power gain is equal to the voltage gain because the current gain is 1. So you have to multiply this with the current gain, which is 1 itself. What are cascaded amplifiers? So cascaded amplifiers, you can see so many amplifiers which are connected in series, and these are the BJT amplifiers, each with its own characteristic voltage gain denoted by AB1 to ABN. So there are basically n cascaded amplifier which are taken here. So the overall voltage gain AB dash will be the product of the voltage gain of each individual amplifier. Usually this voltage gain is expressed in decibels. So we can have 20 log of the gain, whatever we get it, we want to put it in this expression. So this is what we get the voltage gain in the decibel. So the total voltage gain in decibel is basically the sum of the individual gain. So if we find the dB of the first amplifier, the decibel of the second amplifier, and so on till the nth amplifier, the voltage gain, then that would give us the total voltage gain. And this voltage gain, what we get is in dB, which is mostly used in cascaded operation. What are differential amplifiers? So differential amplifier will produce an output based on the difference between the two input voltage. So as the name suggests, it is differential. So it means that we need to difference of the two input voltages. So two input we will be having in differential amplifier. So there can be two modes of operation. One is known as the differential mode and second is known as the common mode. Differential mode inputs are different, whereas common mode inputs are same. And it is key in the operational amplifier application. It will have two input and two output. So here we can see that there are two BJTs, Q1 and Q2, and the input 1 is given to the BJT 1 and input 2 is given to the BJT 2. Output we are taking from the collector of BJT 1 and the output 2 we are connecting from the collector of second BJT. So the basic operation of this differential amplifier, the first category, if we see, if both the inputs are grounded. So here you have the transistor Q1 and the other transistor Q2, and if you can see, the base is basically grounded. So we can specify that both inputs are grounded. In that case, the current which is flowing in the emitter of each individual transistor will be nothing but IRE by 2. So whatever the current is coming from here, which is IRE, this will be splitted up as in accordance with KCL. And since there is no resistor involved, so it will be having the same current. Whereas this current IRE can be computed from the Ohm's law equation. So there is a difference of the voltage. So this is delta VE, which is supply voltage minus the emitter drop divided by the resistor of the emitter. Collector current is approximately equal to emitter current, and two collector currents will be again approximately equal to IRE by 2. So again, the voltage of collector 1 and collector 2 will be again equal, and which is equal to VCC minus the drop in each individual resistor of the collector. The second case what we can take is basically the bias voltage on input 1 and input 2 grounded. So here we can see that the base bias voltage is there in transistor Q1 and transistor Q2 is basically grounded 0 volt. In that case, what happened in Q1 and Q2 transistor? So if the biasing is applied in Q1, which will increase the voltage of the base, collector current IC1 will increase. Here IC1, which is coming from the output of the transistor Q1. Then the emitter voltage, which is equal to the base voltage minus 0.7 volt. So this is the forward voltage drop for the transistor. Q2, if we see, because the base is at 0 volt, it will have a reduced forward biasing and IC2 will decrease. So this IC2 current from the collector 2 will fall because you do not have any biasing applied to transistor Q2. So the overall result, IC1 will increase, VC1 will decrease, IC2 will decrease, so VC2 will increase. So this is the overall effect. The third category that we can discuss is when the bias voltage is applied on input 2 with input 1 grounded. So this is the reverse one. Here we are applying the base voltage to transistor Q2 and 0 volt which is grounded in transistor Q1. So what is the effect of these positive bias voltage? The positive bias voltage will cause Q2 to conduct more. Previously Q1 was conducting, now the Q2 will be conducting more, resulting an increase in the current IC2. So IC2 will increase. The emitter voltage of Q2 is raised. So whatever the voltage we have in the emitter for the transistor Q2 will increase. Now what is the impact it has on Q1? The raised emitter voltage will reduce the forward biasing of Q1 since its base is held at ground. Now here you have the base at ground potential and the emitter voltage has increased. So it will reduce whatever the forward biasing is applied on Q1 because it is at grounded. This causes a decrease in IC1. So IC1 will fall. This is again the reverse of what we have seen in the previous case, case number 2. The increase in IC2 will result in a decrease in VC2 decrease in IC1 will result in increase in VC1. This is the final outcome of the third case, which is just opposite to the case number 2. There are 3 modes of operation when we apply a signal. So one can be single-ended differential input, other can be double-ended differential input, or the third one can be common mode input. These key role what we need to amplify the desired signal while rejecting the unwanted noise. So when we want to remove the noise from the signal and amplify the desired signal, we basically go with these modes. Let us see the first mode, which is single-ended differential input. So here one input is grounded and the signal is applied to the other. Now 2 cases can be there, case number 1 and case number 2. Case number 1, when the signal is applied to input 1. So here you have transistor Q1 and Q2. Q2 is grounded and Q1 is given the biased voltage. So this is case number 1. Case number 2, if you see, this is grounded, the Q1 transistor, and the supply voltage is connected to transistor Q2. So 2 possibilities are there, which we have discussed in the previous case also. So what happened with case number 1 and case number 2? In the case number 1, you will be getting inverted amplified signal at output 1. So this is what the input we are applying in the base of Q1. So the output that we are getting in the transistor Q1 is inverted and it is amplified also. Whereas the output 2 that we are getting is non-inverted amplified signal. So if you see here, with this signal, it is non-inverted and it is amplified. On the second case, if you see, when we are applying at output 2, we get inverted amplified signal. So this is what we have the input. Output we are getting inverted and amplified. And here in the first case, we get non-inverted amplified signal in the output 1. So this is single-ended differential input. Double-ended differential input, we have 2 opposite polarity. Opposite polarity means out of phase. Signals which are applied to both the inputs. So here you can see this is input 1 and this is input 2. Both are applied, and if you observe the signal polarity, these are just out of phase with each other with 180 degree. Each input will affect the output in this case because you have 2 input. So each input will affect. What happened with input 1 alone? So input 1 alone will produce certain output signal. Input 2 alone will produce another set of output signal. And then we can apply the principle of superposition to find the net result in the final output signal. So here we can see that the output when only input signal 1 is there. So here you have input 1 and the other one is at 0 volt. Second case, you have the input 2 and here you have 0 volt in transistor Q1. So when you have together both the input, then it is basically superposition of the output of 1 and 2. Common mode, if you see here, identical signal in terms of phase, frequency and amplitude is applied to both the inputs. So here if you see, this is V1 and this is V2. Both are identical in terms of magnitude, phase and frequency. Then what is the effect? Input 1 alone will produce signals of opposite polarity at the output. So this is input 1. You are getting opposite polarity at output signal. Input 2 alone does the same. So here you have input 2 and the first one is grounded 0 volt. So again this is inverse. When both the signals are applied, they cancel each other. So common mode, you will be getting cancellation of the output due to the inversion of the input signal at the output terminal. The importance of common mode rejection that we have seen here in common mode, it eliminates unwanted signal in the form of noise appearing on both the input. So if there is a noise, it will cancel that noise because both are opposite to each other. The noise sources may occur because of radiated energy from adjacent lines. 60 Hz power line interference can be there. Other electromagnetic sources can be there. So it will enhance the signal integrity in communication and instrumentation application. So in communication and instrumentation, you have to remove this unwanted noise. Hence, common mode rejection plays a very important role to remove other sort of disturbances. What is common mode rejection ratio then? So, the desired signal appear on only one input while the other opposite polarities on both the input that we have seen. These desired signals are amplified and appear on the output. Unwanted signal in the form of a noise appearing with the same polarity on both the input are cancel each other. Hence, the measure of an amplifier's ability to reject the common mode signal is known as common mode rejection ratio. So, common mode rejection ratio is basically we are taking the ratio between the difference and the common mode. So, if you have the high CMRR, common mode rejection ratio, it means high differential gain and low common mode gain. And it is also expressed in decibel as taking 20 log from the previous CMRR. So whenever you have a noise signal in communication and interferences, then in that case, common mode will play a very important role in the differential input to cancel out the noise signal. So this completes our discussion on BJT amplifier. In the coming lecture, we were going to discuss a new topic on the electronics. Thank you for now.